In this problem, we're finding a Taylor expansion of cosine x near x equals pi over 2. So when we propose an expansion like this, what we're saying is we want to represent our function as a polynomial with possibly infinitely many terms, but written in this special way as powers of x minus pi over 2. And this series proposal that we just wrote down is guaranteed to converge very aggressively when x is close to pi over 2, because these terms all become very small and higher powers of them become smaller still. So as it turned out, and I'll post a link to the derivation, the CNs can be found by computing successively higher derivatives of the function that we're working with and evaluating them at the point of interest, which is pi over 2 in this case. So it's going to be the nth derivative evaluated at pi over 2 divided by n factorial. So I'm going to make a list of higher and higher derivatives of the cosine function, starting with the function itself. The first derivative is negative sine x. All right, so there's f together with its first 5 derivatives, and then I evaluate them at pi over 2. Well, the cosine of pi over 2 is 0. The sine of pi over 2 is 1, so the second term is negative 1. The third term, second derivative, vanishes. F triple prime of pi over 2, that's 1 because the sine of pi over 2 is 1. Fourth derivative vanishes. And my fifth derivative, I made a sign error. I missed a minus sign in there, so let's fix it right now. All right, and this means C0 is equal to 0. C1 is going to be a negative 1 over 1 factorial, which is just negative 1. C2 is 0. C3 is going to be 1 over 3 factorial. C4 is 0. And C5 is negative 1 over 5 factorial. Now we can write down this Taylor expansion of the cosine function. Cosine x is equal to negative 1. So I'm looking at this term right now. Negative 1 is C1 times x minus pi over 2. The next surviving term is C3, so I have plus a 1 over 3 factorial x minus pi over 2 cubed, and then minus a 1 over 5 factorial x minus pi over 2 to the fifth plus dot dot dot. Then we're asked for the first 3 non-trivial Taylor polynomials, and all I meant by that was I don't want to have any copies of Taylor polynomials by including one more term that's equal to 0. So I kept exactly enough of this to get these 3 Taylor polynomials. What we're saying is if x is close to pi over 2, then higher powers of x minus pi over 2 are contributing less and less to the sum, because high powers of a very small thing are even smaller. So we can come up with approximations of the cosine function by truncating this series in different spots. And the first approximation is the linear approximation. So when I make a graph of the cosine function together with this function, negative quantity x minus pi over 2, this linear approximation should line up really well, provided we stay close to x equals pi over 2. So let's bring in a picture of that. And it looks like it works out nicely. This is pi over 2 right here. I can tell because the cosine function vanishes there. And I have a linear approximation of the cosine function that's lined up super nicely with the cosine as long as I stay between these values right about here. So I have to be pretty close to pi over 2 for this to be a good approximation. Let's bring in the next approximation. So I could say the cosine is approximately equal to, well, the first term together with the second term. And since all the terms after that are less than the ones I've shown, this should be a fair approximation of the cosine function near x equals pi over 2. Let's bring in a picture of this cubic approximation real quick. So in this picture, the green squiggle is my cubic approximation to the cosine function near pi over 2. Again, pi over 2 is right here. And I can see that this approximates the cosine function very well from about here to about here before I can detect any kind of separation between the two graphs. So this nice convergence to the cosine function is spreading out wider and wider as we keep additional terms in our Taylor polynomials. In particular, this approximation is way better than the first one because it actually captures some of the curvature of the cosine function. Of course, we can improve things by keeping all the way up to the 5th power. And 5 factorial is 120. I'm just going to go ahead and write it that way because I'm about to type in a computer. All right, there's my 5th power approximation. Let's bring a picture of that in real quick. And there's pi over 2. And I can see that the interval on which these approximations are accurate just keeps growing. There's no visible distinction between the two curves all the way out to here now. And I've captured the curvature of the cosine function basically on 0 to pi almost perfectly. You could continue this way for hundreds of terms and eventually just build a perfect cosine wiggle on an enormous interval using polynomials.